We're back, everybody, to the last day of lecture. We only have about 4 problems left, and then after that, we can go over these silly ones here. They're useful, but usually speaking, you don't. I mean, I think I tried to change them up actually. Now that I think about it, so maybe they would be valid to go over. But then any additional time after we go, any additional time after that. I wanted to open it up to any review. I've got the review printed off. The solutions will be posted a little bit later today. But I wanted to make sure we had time to go over that if possible, just a little free review because we're already ahead of schedule, which is awesome. So going back over real quick, the 2 different processes for doing the fundamental theorem of calculus on an integral substitution problem. You can either change the bounds right from the start, or you can keep the bounds as x's and then convert your thing back to x form and then do the fundamental theorem. It doesn't matter which one you choose. Both of them are valid. I would say that option 1 tends to be faster, and option 1 tends to be very, very nice for trigonometric substitution. But option 2 seems a little more comfortable because it's exactly how we've been doing all of the integral substitution problems up until this point, right? You find the antiderivative, you convert it back to x's, and then compute. Like that's how we've been doing it all this time. You find, like, you convert it to a du integral purely in terms of u. You find that antiderivative because it should be nice and neat. Then you convert it back to x's. So that is the appeal of option 2, is that you get to go back to x's and continue the same process. So if you like that more, please be my guest. The difference with option 1 is that you don't need to do that. So you save on time and space and carpal tunnel, right? You avoid some carpal tunnel. So long as you remember that you've made the changes to u bounds. So I feel like it would be a good idea to, at least for these first 2 or 3, that I show you both methods side by side. So we'll do it option 1 and option 2 on all of them to see which one you prefer. So this one here, the definite integral from w equals -1 to w equals 2 of 12w minus 10 times e to the 3w squared minus 5w. So I'm actually going to do, I'm actually going to do the u, du, and all that stuff at the very top on the right-hand side, just because that happens for both. Both times, it doesn't matter what you do, you have to do the u substitution because that's the only way to find the antiderivative. So what should u be? The 3w squared minus the 5w, the thing inside of the exponential. Exactly right. So 3w squared minus 5w, and that would mean that du would equal 6w minus 5 times dw. Remember, there's the whole thing has a dw. The whole thing is multiplied by dw because of the intermediate step that's happening here. Just as I know I've sounded like a broken record, but I don't want this to happen. I've seen it happen too many times where students don't put the parentheses, and then they think that the dw is only attached to the 5. And that will throw everything off. The reason why it's all being applied to that is because what you have is you have du dw is equal to 6w minus 5, and then you're cleverly multiplying by dw. That's why the dw is applied to everything. I just don't want you to make that mistake. It's a vicious, it's a surefire way to get you flustered during an exam, and that's the last thing I want you to be on an exam. I want us to be calm, cool, and collected. So that's that, which means that dw, remember the last step is to solve for the dw. That'd be 1 over 6w minus 5 du. That step is consistent across both options. Now we'll actually do the 2 different options. So I'll split it right down the middle. Right down the middle. That right in the middle. Right there should be fine. No, that's too. There we go. Okay. So option one, to change the bounds. Change the bounds. So I'm going to I'll highlight them. Let's do red for the bottom, green for the top. This one, the reason why I want to caution us on this one. So bottom bound stays bottom, top bound stays top, no matter what number you get when you substitute it in. And you'll see what I mean. So if x is equal to 2, then u will equal 3 times 2 squared minus 5 times 2, which ends up being 3 times 4, that's 12, minus 10, that's 2. Did I change the bounds in this one? And then if x is equal to 1, negative 1, excuse me, then u will equal 3 times negative 1 squared minus 5 times negative 1. That will be 3 times 1, so 3 plus 5, which will be 8. So the integral becomes the integral of the definite integral from u equals 8 to u equals 2. That is okay. It looks weird, but the bottom bound stays the bottom bound, the upper bound stays the upper bound, regardless of if it changes size. So this becomes that integral, and then it's times 12w minus 10. That doesn't go away. Remember, because that's not what u is. U is equal to the exponent of the e. So it becomes e to the u times 1 over 6w minus 5 du. So let's recap, because this is kind of weird because we're doing it a little bit different than we've normally done. Regardless of the format, you have to do the u substitution itself. So we did that up here. We got the dw is equal to 1 over 6w minus 5 times du. And then if we're doing option 1, we're changing the bounds to u bounds. And so the upper bound was 2. So when I plugged that in, I got that u is also equal to 2, just kind of by happenstance. Just so happens that it works out. And then when I plug in the bottom bound, the lower bound, x equals negative 1, I get that u will equal 8. So the new integral is from u equals 8 to u equals 2. That is okay. The fundamental theorem of calculus, if you go back to it, way back when, where are you? Where are you? Right here. Notice that it doesn't really specify that a and b needs to be, like, I mean, technically speaking, it does, but it actually ends up not mattering what a and b are. The definite integral works regardless of what a and b are. So we don't need them to be in order for it to be computed. Any questions on that? So yes, the bounds are all wonky, but that's okay. That's totally fine. And then you might be like, well, Phil, that doesn't work out. This does. The 6w minus 5, yeah, it doesn't cancel with the 12w minus 10, at least at first. But if we notice that this is 2 times 6w minus 5, then the 6w minus 5's cancel. We have the integral from 8 to 2 of 2e to the u du. The antiderivative of e to the u is itself. And remember, these are u bounds. So we don't need to do anything else. We just go, this is 2e to the u evaluated from 8 to 2, which would be 2e to the second power minus 2e to the 8th power. And that is where we'll leave it. Yes, it does look weird, but you have to understand that this, I know that, like, we're so used to seeing our definite integrals be positive, but remember, a definite integral can be negative. If your function is below the x-axis, which this curve is up until, let's see here. up until 5/6. So from -1 to 5/6, it's below the x-axis. Like if you were to draw the curve from -1 to 2, the curve looks, I don't know what the shape looks like, but it basically looks like, and here's 1, here's 5/6. Up until here, it's below, and then it becomes up. So it's natural for this thing to be negative. That is okay. It is okay for a definite integral to be negative. Area, always positive, right? We talked about that in 4.2. Area is intrinsically a positive idea, but you can be below the x-axis. A definite integral can be negative. Anywho, next one. That's option 1. Option 2 is to keep the bounds in terms of W. But remember, you have to add that W equals for your bounds. If you're going to change the variable, the bounds need to specify that they are W bounds. So this is equal to the integral from W equals -1 to W equals 2 of 12W minus 10 e to the u times 1 over 6W minus 5 du. And the same process does happen because we're like, regardless of how you do it, you still have to find the antiderivative. Nice thing, once again, this is 2 times 6W minus 5. The 6W minus 5's cancel. We've got the integral from W equals -1 to W equals 2 of 2e to the u du. Integrating that because we can, it's an integral purely in terms of u. So this is 2e to the u evaluated from W equals -1 to W equals 2. But those are W bounds, so we need to convert our integral back in terms of W. So this is 2e to the u, or 2e to the 3W squared minus 5W evaluated from -1 to 2. Once again, I've dropped the W equals because I've got it back in terms of the actual variable in question. And so this becomes 2e to the 3 times 2 squared minus 5 times 2 minus 2e to the 3 times -1 squared minus 5 times -1. And lo and behold, you get the exact same thing. You'll get 2e to the 2 minus 2e to the 8. It's essentially the same thing. It's just whether or not you're plugging it in at the bottom or plugging it in at the top. It's whether or not you're plugging in the W bounds here or plugging them in up here. It doesn't matter. Hopefully that's not confusing and more beneficial to see which way you're liking more. Yes. Excellent question. So when should we simplify? So I'd like you to leave these things in exact form. Specifically, if it is anything that has just a number or something that is nicely computable. So if you plug it in your calculator and it gives you a finite fraction or something like that, that I want you to compute. But if you get e to the second power, e is rational. So e to the second power, e to the eighth power, those give me finite, like irrational numbers, leave them as is. But if the thing was 2, so the kind of the rule of thumb, come on, is this thing dead? I think it might be dead. Well, I need to wait for that to charge. If it has like a square root of 9 on your exam, write as 3. If it has e to the 0, write it as 1. Tangent of 0, write it as 0. But if it's like tangent of 3 radians, leave it as is, because tangent of 3 radians isn't a nice number. But if it's a number that we know that we can compute it. Does that make that's the rule of thumb here. So any other questions on option 1 versus option 2? All right. Then we will do this one. Let's try it for the for this next one and then this one. let's go ahead and, ooh, that one's going to be tough if we don't do it properly. We'll get to that. So for this one, well, like, just out of curiosity, which method do you guys like more? Option 1? Option 2? That's split. Interesting. That's awesome. As I said before, though, once again, it doesn't matter which one you choose. I will give you, like, both are completely valid, so both will get full credit if this problem pops up on the exam. So, what? I mean, I don't think it's a surprise that there's going to be a definite integral on there. I'm not saying, like, it could just be a basic definite integral, like one that doesn't require U substitution. It could be one that does. It could be one and another one, like one that doesn't require it, one that does. You never know. I can neither confirm nor deny the existence, but I would tell you, like, if I was a student, I would be banking on it. I would be expecting it because it's a big concept, especially considering, as I've tried to really hammer on the head, that this is going to be central to Math 182. If you do not know U substitution, you will be screwed. Like, I'm not going to sugarcoat it. I've taught Math 182 several times. The students who don't remember U substitution always end up doing worse. So that's why I want to remind you, please, if you're planning on taking 182, please this summer, like week before classes start, just brush up on U substitution. You will be so thankful that you did. You will you will go into that semester far more prepared. Even if you like remembering your derivative rules and your integration rules, those things take time to like kind of get back into the swing of things. But U substitution is going to just be happening all over the time. And if you don't know how to do the U substitution, everything falls apart. It'll be happening on a daily basis up until about week 10. So I'm really trying to prepare you guys for that. This next one, I think I'm going to do it. Do you guys want me to do it in both ways again? Or can I just swappity swap? A swappity swap, not a swap.
Yeah.
Okay, there we go. We gotta use the Gen Z lingo, right? That swappity swap, that's a Gen Z, or is that just is that millennial lingo? It's just me. It's just me. Fair enough. Fair enough. All right. So this one, I'm gonna do option 1. I'm gonna do option 1 on this one. So what should U be? Because if we look at this thing is not an easy to compute integral. It's not one of the basic integrals. So we have to do a U substitution. The denominator is always a good option. We'll see if it works. If it doesn't, we'll go back to the drawing board. It will work, but still. U is equal to 2 plus sine of t. That would mean that du is equal to cosine of t dt. Meaning that dt is equal to 1 over cosine of t du. And then I'm going to make sure the bounds stay where they are. It could be that the bounds change. It could be that they stay the same. Or like it could be that they stay increasing, like the bottom one is lower than this top one. It could change. We don't know, but let's just work with it. So if t is equal to pi over 2, then u will equal 2 plus sine of pi over 2. And sine of pi over 2 is 1. So that's 2 plus 1, that's 3. That's going to be our upper bound. And then if we do t equals 0, you will get that u equals 2 plus sine of 0, which is 2. So this integral then becomes the integral from 2 to 3 of cosine of t divided by u, because that's what we claimed u to be, times 1 over cosine t du. And lucky for us, the cosine t's cancel. We have that this is the integral from 2 to 3 of 1 over u du. And once again, if you feel comfortable skipping algebra, please be my guest. If you feel comfortable skipping a few steps, like the cancelization going from here, like skipping the cancelization and just going to 2 to 3 of 1 over u du, please feel free to. In addition to that, just talking about like writing on the exam, I'm writing this for our notes to see how everything happened. If you want to plug this in your head or just plug it in your calculator and then and write it down, that is fine too. It's just so that when you're looking at your notes, you're like, that's what we did. We plugged it in to change the bounds. So those are u bounds. So this becomes the integral of natural log of the absolute value of u evaluated from 2 to 3. And that would just be natural log of 3 minus natural log of 2. Or if you really want to be cheeky on the exam, you could write natural log of 3/2. Because of the properties of logarithms. If you want to be clever. And I'll write on your paper, ooh, nicely done. Remembering your properties of logs. But that's that would be using option 1. I guarantee you, like if you do it with option 2, if you like that method more, it'll get you the same answer. Any questions on that? I'm going to skip this one because this one is an inverse trig integral that requires a little special case. This one you would be able to handle in Math 180. This is one you might see in Math 182. So that's why I'm going to skip this one and we'll go to this one. Looking at this, I want you to try it. I want you to try it. You're stumped. It's okay. This one's a little bit tricky. It's something we did last on Monday. As a little hint, I'm trying to make it a thing. Right? Terminal, like this type of an integral is something I'm trying to make into a thing. I'm trying to call it something. By the way I'm doing this one is I'm going to be doing option 2 where I keep the bounds the same. I'm going to keep them as x bounds. Just so we get practice with both. Oh, I don't know why it became a 1, -1. Thank you for catching that. Thank you. I'm looking at the experts too. That being said, by the way, on the exam, if that's an easy mistake to make, you probably get full credit as long as you followed it through. Without reverse engineered U substitution, I don't think there's a way. Yeah, I don't think there's an easy way to do this without doing it. You could resort to, in 182, you'll learn about Taylor polynomials, and that might be able to fix it. But as it stands, nah. Sadly. And yes, I know it has fractions. I know it has fractions. It's okay though, guys. It's okay. Fractions are fine. They're good buddies of ours. Promise you it works out nicely. I promise you it will actually be a nice integer number. I know it doesn't look like it. It's like all the great stories. All the great stories, Mr. Frodo. Full of darkness and danger they were. You didn't want to finish them because how could it be happy? If anybody knows what I'm talking about. Lord of the Rings reference. Two Towers. It will look out. It will work. It will work. Trust me. Two plus two. 15. 6 plus 10. 16. 15. Right? What am I doing? What happened to the 3? Oh! Why did nobody catch it? That should be a 2. So sorry about that if you were following along with me. No, 10, 12 or 5. Let's talk through it, especially since I made that stupid error. This is an example of why I don't really like to use option 2 unless I have to, because now I have to like rewrite it as x minus 2 to the fit. Like it takes a little bit longer. Whereas if you leave it, if you change the bounds, and this is just the integral from 0 to 1, and it becomes a lot faster. But at the end of the day, it will not matter too much. So this was a reverse engineered U substitution. We made the, like, as I was talking about last time, the good news about reverse engineered U substitution is it obeys the same typical choices of U that we've already been accustomed to. You should always choose a U to be in a denominator or inside a radical or a large power or inside a function. And so this works out in our favor this time. The x plus, so you get U equal to x minus 2, the inside of the radical. That would be a good choice of U. If you solve for it, you get du is equal to dx. And then you get x plus 1 times the square root of U. And that is a situation where you're like, well, it didn't really do, like, I still have x's in it. So you can go back to the drawing board, but if you look at it, and this is a very, very good thing to know about moving forward in your mathematical career, in case you don't already know this already. Your teachers design the exams so that they're solvable, right? There's got to be a way to do it. So if you try this one and notice that nothing happens, try using u equals x plus 1. It won't get you anywhere. I promise you, it won't get you anywhere. But you can still try. And then maybe try doing the whole thing. It'll get even worse. But that's okay. That happens. So it must be one of those three options. It must be either u equals x plus 1, u equals x minus 2, u equals the square root of x minus 2, or the whole thing. And as long as you're willing to stick with it, you'll see that this is the only option. And then you've exhausted everything, so this must be a reverse engineered u substitution. You start to notice it when it's going to be that is if the degree on the outside of whatever polynomial you have is greater than or equal to the degree on the inside. So that is how we do that one. Are there any questions on it? So we make the u substitution, then we solve for x in terms of u by adding 2 to both sides. That is completely legal because we're just taking an equation and adding 2 to both sides. That's completely legal. And then we replace u plus 2 with like x with u plus 2. That gives us u plus 3 times u to the 1/2, which I mistakenly forgot to. I just wrote u to the 1/2 instead of 3u to the 1/2. The bounds are still in terms of x if you wanted to use option 2's method. And then distributing in that u to the 1/2, because it's already by itself, you get u to the 3/2 plus 3u to the 1/2. You integrate those, you get u to the 5/2 over 5/2 times 3 times u to the 3/2 over 3/2, which from x equals 2 to x equals 3. When you flip and multiply, that's why it's 2/5 times x minus 2 to the 5/2. And then 3 times 2/3, the 3's cancel. That's why it's just a 2 times x minus 2 to the 3/2. Plug in the 3 and plug in the 2. You get 1 for the first entry, 0 for the second. It gets you exactly what you want. Any questions on that? Okay. So I'm going to go backwards because these ones, so I'll show you this one right here, 4.6.4a, not a, I mean, that one's actually, no, never mind, that one's fine. 4.6.4b, that one is a situation where I would not expect you to have to deal with it until 182. These other two, though, these are surprisingly fine. And so let's look at them. So they're involving trigonometric inverse trigonometric functions. So that kind of does give it away, yes. But let's just say, for the sake of an argument, that we went into this and we didn't see this statement. It had nothing, like we were just given this on a final exam and we had to figure it out. We didn't know what it dealt with. We try several things and see what happens. It's okay if you're wrong. If you're wrong, the worst thing that happens, you erase it, you try again. I will have plenty of scratch paper with me for the final exam. So if you want to just go bananas and try 80 million things, that's okay. So for this one, I'm going to go approach it like I was you, like I was a student in Math 181, and I had never seen this before. My initial gut reaction would be to make u equal to the denominator, the inside of the radical in the denominator. That would be my guess. U equals, oh, wrong size font. U equals 1 minus e to the 2t. Well, then by the chain rule, du would equal negative 2e to the 2t dt. So dt would then equal negative 1 over 2e to the 2t du. And you'll see why this becomes a problem. So it's going to be, so the negative is sticking around, and then it's going to be e to the 2t times 2. Yes. So if we do that, this will then become the integral of e to the t divided by the square root of u times negative 1 over 2e to the 2t dt. And so it doesn't cancel nicely because it's not e to the t, it's e to the 2t. Now that's okay. Like, here's one observation is that e to the 2t, that's the same thing as e to the t squared. Because remember, when you have power raised, like a power raised to a power, you multiply the powers. So yes, you could cancel one of the t's, but that wouldn't get rid of the whole thing and cause problems. So this is not the right call. One option then, and this actually might end up working. It might end up working. Would be to make u equal to the numerator. U equal to e to the t. And in fact, that will be the right answer. And the reason for that is if I rewrite it like this, if I rewrite it like that, e to the 2t is the same thing as e to the t squared. There's an integral that we've seen that looks like that in the denominator. You guys remember that? That's sine inverse. So this ends up being an inverse trig function. So we end up making u equal to e to the t, then du is equal to e to the t dt. So dt is equal to 1 over e to the t du. I wrote that quickly, so I'll slow down. Mainly because I just love finding new circumstances that we haven't seen before and just figuring out what to do in that circumstance. You learn something new every day. The best part about being a human, at least in my opinion. That and Good Pies grandma style pizza, by the way. Right? You know what I'm talking about. It's amazing. If you haven't been, it's in downtown Las Vegas. Good Pie. They have the grandma style. It is the best pizza you'll have in Vegas. It's just called Good Pie. That's the name of the place. It's expensive as all get out. I don't like mushrooms, so that's. But I imagine if you do like mushrooms, it's probably good. But I highly recommend it if you've never had it before. It's pricey, but it's worth it. It's very, very good pizza. Anyways, they also do Detroit deep dish, which is one of my favorites. So this now becomes the integral of u over the square root of 1 minus u squared times 1 over e to the t du. Because remember, u is equal to, this is a classic, like, e to the t is equal to u. And so it looks like it doesn't cancel, but e to the t here, that's u. This is u. So they do cancel here. And we have the integral of 1 over the square root of 1 minus u squared du. And that is a integral that I do know. That's sine inverse. Sine inverse of u plus a constant c. That's going to be sine inverse of e to the t plus a constant c. Going to show you that this problem is meant to show you that sometimes rewriting things in a different format can bring you ideas. So e to the 2t being e to the t squared is something we can do. In a similar fashion, this one right here. The good news is it does kind of obey what we know, right? If you want to choose a typical choice of u, a good option would be something in the denominator. The whole denominator, if you tried that, you'd see that it becomes kind of nasty, right? If we made u equal to the whole thing, u equal to w times 1 plus natural log of w quantity squared, du would then be, by the chain rule and the product rule, it would be 1 times 1 plus natural log of w quantity squared plus 2 natural log of w over w times w, all times dw, which doesn't look like it's going to get us anywhere. So I'm going to stop and say, you know what? If it really ends up being that's the choice, then I'll come back to that. That seems like it's not going to work. You'll start to realize that, just like you would any other thing that you get comfortable with. So then maybe you try and do u equals 1 plus natural log of w quantity squared. So that du will equal 2 natural log of W times 1 over W dW. And that will get you somewhere, right? So that would mean that dW would equal W over 2 ln W, just du. And you'll see that this is not going to work out anyways, but you'll get W times U squared, or just U, times W over 2 ln W. And sadly, nothing's going to happen. Nothing's going to happen because the W's will cancel, but that ln W is still around. So what haven't we tried? Just natural log of W. Why not? And that does kind of obey what we've learned for typical choices of U. Something inside of a larger weird power. Yes, second power is not that large, but still. Something inside of a power is a good option. So let's make U equal to natural log of W. Then du will equal 1 over W dW. So dW will equal W du. And this will equal the integral of 5 divided by W times 1 plus U squared times W du. The W's cancel, and we're looking good. We got 5 over 1 plus U squared du, and that is an inverse trig function. That's tangent inverse. The 5 can be ignored. It's constant. So this is 5 tangent inverse of U plus a constant C, which would be 5 tangent inverse of natural log of W plus a constant C. Would I have expected you to get this right off the bat? No, absolutely not. But now we've seen it before. Now it's not taboo. It's not something we haven't experienced. We're now more prepared for it. And I'll say it one more time though. I'm not saying this stuff is easy by any means. It's honestly, in my experience, it's the hardest hurdle for students in calculus, is getting over that hurdle of being okay just messing around with things. You'll find, especially with Legos, much like Legos, the more you experiment, the cooler things that you learn how to do. You get to make super cool shifting wings and stuff like that just by realizing you can mess with the pieces the right way. That's the best way to play. You probably disagree that these are like Legos. You'd be wrong, but anyways. So these two I wouldn't worry about. Part A, the answer would be to split it up into 2 pieces. It'll be nice and quick if you do that. Esther, did you have a question? It's not that it's unsolvable. It's just you're going to learn how to take care of that in 182 with a much faster thing. And I know we love to haze you in mathematics, right? We made you find the vertex of a like the maximum of a parabola in Math 126 by using that terrible formula, but now we have calculus that can make it done way quicker, right? But in this case, it's way more complicated to teach it this way than it is to learn trigonometric substitution. So I'm not even going to bother. And I know I can say definitively that type of thing. This may be fair game. This problem here may be fair game. Part B, maybe. But this one would be a cruel joke. So anyways, that completes our notes. That completes all of our notes. One thing I forgot to mention when we were talking about the evaluations. Once again, I hope you've been able to complete them. I'm sorry if they're constantly pestering you about it. One thing I'm always looking for is like critiques on my stuff. If you have any recommendations on how to improve the notes, please let me know. I'd love these things to be perfect. I know there's never a chance for this thing to be actually truly perfect, but if there are things that I can do to improve it, like if you think that there needs to be more space on problems, or if you think there's room for trimming down things, please let me know. I'm happy to hear that. Okay, so let's take a break until 10 13, 10, 10, 14, 10, 14. I'm going to pass back old quizzes and stuff. And then we can do review for the rest of the time period. People watching the recording, go do some guided meditation. We're back. And so the remainder of the time is for any questions you guys have, whether it be about these things, something else you want to do, or about general questions about the final exam or anything like that. I'm happy to answer anything.
It's same time as class.
That is correct. Good point. So unlike UNLV and a few other colleges, since it's a community college, we actually there was a huge debacle about whether or not we have a final exam schedule. Because like most colleges do, but because we are a community college and we have a very large secondary student population that have jobs and everything like that, it's a lot harder for them to get 2 hours off to do an exam. So that's the reason why. So yes, our exam will be at the exact same time that we have class. So it'll be in less than a week time. It will be on Monday at this exact time. It will be roughly the same length as the normal exams. I think if memory serves, it's a little bit more questions, but a lot less multi-part. So. Related rates? Sure. So that's actually a good thing to talk about here real quick. Did I not put an optimization problem on here? Okay. So look at the difference between question 9 and question 14. So question 9 says, rather hard to swallow multivitamin is cylindrical in shape. We're not going to yes, it's technically speaking, it's a cylinder with like 2 half spheres on top and bottom, but let's just assume that it's perfectly cylindrical. The pill has a height of 17 millimeters and a diameter of 2.4 millimeters. When the pill is ingested, the stomach acids start to break down the pill such that the volume is decreasing at a rate of 13 millimeters cubed per second, and the height is decreasing at a rate of 0.8 millimeters per second. Find the rate of change of the radius. Versus question 14. A farmer needs to enclose 2 plots of land with 10 kilometers of fencing. Based on the needs of the farmer, 1 plot needs to be circular and 1 needs to be square. Find the dimensions that maximize the total area. There are keywords in those problems that tell you what method to apply. 14 is an optimization problem because it says maximize. As soon as I saw that word maximize, or the word minimize, or largest, or smallest, or biggest, or tiniest, or whatever like that, any of those words that quantify a size of something or maximizing, that it means it's an optimization problem. Versus this one has the dead giveaway of rate of change. Find the change in the radius, or find the rate of change. As soon as you see that, related rates. So this problem, let's go ahead and I wonder if will it let me copy this? I wonder. In the words of what's it called? The words of Sesame Street. I wonder, what if, let's try. Sweet. All right, it did work. So when it comes to word problems, regardless of both ones had the same first starting point. It's to read the problem, which we have done, and then to draw a picture if you can. So this is a cylindrical pill. And before I get anybody trying to draw me a non-right cylinder, it's not like that. It's a right, oh, did you mean to do a right cylinder? Yes, I did. It's like this. And we know that the original diameter is 2.4. And its height originally is 17 millimeters. Maybe that's going to be useful. Maybe it won't. We don't know. What we do know is that the stomach acids are breaking it down. So the radius is going to be changing, the height is going to be changing, and the volume is going to be changing. And we're assuming that it's acting efficiently on all facets of it. Yes, it's not actually math like that. That's not how it would actually work, but that's what we're assuming. So we have an unknown radius r because this thing is going to start shrinking. It's going to start shrinking. and we have an unknown height. So we need to, now that we've drawn our picture that's trying to tell us important things, we know that the height is 17 at the start, but we don't know what the height is after a certain amount of time. That's going to be basically the initial condition. We're going to try and find the rate of change of the radius when the pill hits the stomach acids. So we have the know and we have the want. So what do we know? Yeah, we know the initial dimensions. We know a rate. We actually know two rates. We know the rate of change of the volume. We know that dV dt is equal to -13. And we know that dH dt is -0.8 millimeters per second, but like you don't need to write the units if you don't want to. And look, what do we want? We want the rate of change of the radius. We want dr dt. When h is 17 and r is 1.2. Because remember, it said the diameter is 2.4, which means the radius is 1.2. Okay. Problem is, though, I don't have a formula. But I promise you all formulas that are necessary will be provided, and the volume of a cylinder is something we need to have because that's the shape in question. And the volume of a cylinder is V equals pi r squared H. One of the things I'm very, very, very excited for you guys, if you're planning on taking 182, is, and I'm sorry that I won't be able to teach it to you because it's one of my favorite things, you will understand why volume formulas exist. How do we figure out the volume of a cylinder is pi r squared H? You've just been told that since you were a kid. That's the volume. Accept it, kid. You will learn why it works. And that is fascinating. It's very, very fun. But we'll get there. You'll get there. So now we have everything. We have a formula that's relating V, R, and H together. So that's exactly what we need. And we don't need to solve for anything because we know dV dt. So when we differentiate this, we will get dV dt. That's fine. We will get dr dt, which is what we want, and we will get dH dt, which is something we know. So this is going to be perfect. So we'll differentiate with respect to t. The derivative of v with respect to t is just dV dt. Pi is just a constant. But I mean, I suppose we could write it as this is our F and this is our G. Because remember, H and R both depend upon T. Because as time changes, the radius will change and the height will change. So they're both functions. So this is a product of two functions. So we have to do the chain rule, the product rule. We will have to do a chain rule with R squared, but regardless. So F prime would be 2 pi r dr dt times h plus dH dt times pi r squared. Make sure you understand where those derivatives came from. And it's okay to ask. It's been a while. It's been, looking at my calendar, when did we go over that? Went over 2.7 in week 8. It's been 8 weeks. It's been 7 weeks. So it's been a while. So it's okay if you have any questions on how I took those, got that derivative. All right. Well, we know everything here. So dV dt, that was -13 equals 2 pi r. R is 1.2. dr dt is unknown. H is 17 plus dH dt, which is -0.8 times pi times r squared, which is 1.2 squared. And so this is going to be a pretty nasty calculation, like ish. We can always use approximations though, since with these problems, with word problems, I almost always want them to be an approximate answer. I want you to approximate usually to 2 decimal places. So let's see here. 2 shift pi times 1.2 times 17 is 128.17698 DRDT plus negative 0.8 times pi times 1.2 squared is negative 3.61911 so on and so forth. So I'll add that to the other side. So negative 13 plus that is, wait, no, minus that. Wait, what? Okay, there we go. Negative 13 plus that answer. You should get negative 9.3808885 is equal to 128.17698 DRDT. Yeah, I know that. Yes.
It's 17 for the height, not 7. Why, wait, hold on. Because isn't, no. I'm sorry, I wrote 17.
So
Because I thought that it would be different.
so this I need to change the wording next time I rewrite this. I need to edit it to say find the rate of change of radius when the pill hits the stomach acid. So when it is full height. Like that is a problem that I should have specified. I should have said when the height is like when it enters the body, so that we know that it's when it's in its full form. So dividing that by 128.17698 gives us that DRDT is negative 0.0731 So approximately negative 0.07 millimeters per second. Let's see, did I get it right? Nope. What did I do wrong? No. Did I make a mistake? There's a possibility here. There's a possibility that I did it, that I assumed something and I didn't write it down in the original thing. Decreasing at a rate of 13 millimeters cubed per second, 0.8 millimeters per second. V is equal to pi r squared h, so dv is equal to 2 pi r drdt times h plus dHdt times pi r squared. Good. Negative 13 is equal to 2 times 1.2 times 17. dHdt is negative 0.8. Let me, one moment. Let me look at my solution guide that I've posted, like that I'm gonna post, and see what the heck I did wrong. Two pi times 1.2. No, the notes are wrong, so that's good. That's an easy fix. Good news is I haven't posted solutions yet. So this is actually correct. The answer key is wrong. The answer key is wrong. I accidentally put positive 0.8 instead of negative 0.8 in the solution guide. So that would change completely everything. So this is the correct answer. Apologies about that. Any questions on that? So I'm going to actually make a note to myself, if you don't mind. That was question 9, right? Oh. Answer to number 9 Apologies for the delay. All right, back to where we were. Any questions on that? So yes, I will update that and change that to be the correct answer very shortly. But anything else you guys want to do? 11, don't worry about. 11 is not going to be tested upon. I've already talked about that. The Riemann sums not going to be tested upon. But what is the most important thing? So I actually had a student ask me this question. So if I'm thinking about it, what is used in almost everything we do? Derivatives. So definitely make sure, like, if I were studying for this exam, I would make sure my derivative rules are top notch. So I'd go back over unit 2 first, then I try unit 3 and unit 4, and then and also study unit 1 when I have a chance. Because unit 1, I would imagine there's probably a little less emphasis on unit 1 since it's been so long, and everything else is very, very dependent upon derivatives. So I'd spend a bigger time on derivatives. Remember that, as I said before, this is not an end-all be-all list of everything that you'll need to know. Definitely go over your old exam reviews, go over the old quizzes, old exams, make sure everything's working out for you. But you'll notice, like, for example, there's only one question in here that involves implicit differentiation, just question 7, but there's probably room for those somewhere else. I think all of these are very, very good integrals to test out. I think there's a lot of good problems here to try. So some more fun than others. G is probably a nuanced problem that has to do with the absolute value, 2G or 3G, but
Are any of these in here use substitution?
yeah, there's a few like the first 2 don't require use substitutions, but the rest of them do.
Okay.
Question A, by the way, is just to remind you, like, hey, numbers are just numbers. It looks scary, it's just numbers. Pi is just a number. 7th root is just a function. So anything you guys want to do? I mean, I could pick out some stuff if you want. And also feel free, like, if you're all done, you want to go on your merry way, that's fine too. I'm cool calling class right now if you want to. I will stick around until the end of class. And these are some fun problems, honestly. If I'm looking at ones that I'd love to do, I love 3K and 3P. I think those are very fun ones. Especially K. K is silly. You guys want to do K? Is that okay with you guys? Right? Who's that? Squilliam. All right, let's try that. This one right here. All right, this integral. What will be a good option? Within the ln? That could work. That could work. Like, I'll tell you there's a faster way, but that will work too. It'll be a W substitution. But we should like it's totally fine to go that route. If U is equal to wrong size font. If U is equal to B squared minus 1, then DU will equal 2B dB. So dB is equal to 1 over 2B du. So this would become the integral of 4B divided by U times natural log of U times 1 over 2B du. And luckily, the B's cancel, but there's going to be a leftover factor of 2. And so you'll notice that it is an integral purely in terms of U, but it's not perfect because we don't have a formula for 1 over U ln U. But we can still work through it. Just need to do a secondary u substitution. So it's 2 over u ln of u du. What should w be? Throwing out crazy ideas.
I think so. Wait, on.
If you that's I'm glad you mentioned that because that's the classic mistake that students make is to make u equal, like make your variable equal to your other variable. It ends up not changing anything,
Yeah.
but still worth a shot. Hey, you do it enough times, you learn to not do it. You can try and make it u ln u, but I'll promise you that's not going to work out. But we could try it. So, what do you think? What haven't we tried?
Two. Or LNU.
The LNU. The LNU. Why not? It could work out. Then DW is the sister of Arthur, but it's also 1 over u du. So that means that du is equal to u dw. So this equals the integral of 2 over u times w times u du, or u dw, excuse me. Maybe an argument to not use w. It's starting to look a little crazy, but you get 2 over w. That is something we know how to integrate. That's going to be 2 natural log of the absolute value of w plus a constant c. W is natural log of u, and u is b squared minus 1. So this will be 2 natural log of the absolute value of natural log of b squared minus 1 plus a constant c.
What would have been if we didn't do double substitution?
If you had chosen to not do a w substitution, what you should have chosen was u equals ln of b squared minus 1. I encourage you to try that, and it will work out better. Fun fact, so what I told you guys is that anytime you do 2 u substitutions, it can be done in 1. And in fact, if you really want to get mathematical about it, it's the composition of your 2 things. So w of u would be ln of u, which is ln of b squared minus 1. That is your function. It's a composition. It's just a fun little observation, but not required. So this will be the better option. Not wrong to do it this way. But it works out. Just have to be okay with getting your hands a little dirty. But isn't that cool? Natural log of natural log. You can go crazy with these things. It's pretty fun. You can even do one that's like a natural log of a natural log of a natural log. That would be really cool. But I encourage you, like on your own time, try it with that. You'll see that it goes a lot faster. But teach them. Any other things? Do you guys want to go over this problem here? Number 15. 15 is a pretty good one. Interpreting integrals and graphs, because we haven't really talked about that too much. So the graph of the function f is given below. For parts b through e, define g of x to be the area function from -4 to x. So find the following integrals. The integral from -2 to 4. -2 to 4. That's a triangle, right? From -2 to 4, that's just the area of this thing. So 1, 2, 3, 4, 5, 6. It's a base of 6 and a height of 2. 1/2 the base times the height. This is 6. 4 to 8. That's going to be a quarter circle with a small triangle with base 1 and height 3. So this would be 1/4 pi times 3 squared, excuse me, negative plus 1/2 the base 1 times the height 3. That's this quarter. That's a circle with radius 3. That's why it's 1/4 for the quarter, and then the radius is 3, so that's why it's pi 3 squared. And it's a negative because this is talking about an integral, not necessarily area. If it asks you to find the areas of these regions, then the answer would be the positive version.
So it's only negative, it's still positive.
The x-axis, that's correct. Because the definite integral by its construction is adding up the heights of all those rectangles, and those rectangles would have negative heights. So that's the reason why. Then part 3 is basically taking all the pieces and making them positive. Like that. This is the absolute value function. It just takes all the negative pieces and flips them up. So just calculate the area of all four, 1, 2, 3, 4, 5, 6 of those shapes and add them together. You got what you need. Find the following values: g of -1, so it looks intimidating when you first see it, but it's actually very, very approachable. Just what would g of -1 be? G of -1 is equal to the integral from -4 to -1 of f of t dt. That's the integral from -4 to -1. It's this region plus this region. And you're done deal. Any questions on g of -1? Like, we can compute it, but I'd rather spend time doing more problems like that. That's going to be just a calculation after the fact. G, this one I thought was really clever. This one right here, g of the limit as x approaches positive infinity. What would that be? What do you think? Very, very close. So yes, the limit of the limit as x approaches infinity of f. This is the graph of f. So the limit as x approaches infinity of f would be 3. But remember, g is the area function. It's infinity. Because yes, there's a little bit of negative area here. There's a little bit of negative area here. But as this goes on and on forever, you're just going to keep adding up more and more rectangles. Each x value you keep going further, you keep adding 3 more units squared. So this one ends up being infinity. That was part B, part 2. Yeah, it says it right here. Yeah. And g prime of 7. G prime of 7. What is g prime? G prime would be the slope of the area function, but we're not given the area function. We're given the function. But what do we know about the connection between the area function and the function itself? What is an integral? It's a antiderivative. So if you take an antiderivative and take the derivative of that, you get back to the original function. So g prime is just f of 7 because f is the derivative of g. There's that whole fact. That's fundamental theorem of calculus part 1. It equals the integrand. The integrand is the derivative of the area because that's what that thing is trying to tell you is that the derivative of an integral is the original function. They undo each other. They're opposite operations. It's essentially the ddx and the integral cancel each other out. So that's why g prime of 7 is actually f of 7, which is -3. Boom. Super fun problem. Find the critical values of g. Those are think about the critical values of g. Those would be the places where the derivative equals 0 or does not exist. Since the derivative of g is f, that would be -2, 4, and 8. Was this problem on the exam? Yes, it was. I'm very original, I know. So those would be the critical values. And find the intervals in which it's increasing or decreasing. You just answered that on the exam 3 reading. And G double prime of 2. Well, G prime is F, so G double prime would be F prime. Isn't that fun? Isn't this like circular fun stuff? Love it. Oh man, it's such a fun problem. But G, so you'd want to find the slope of the tangent line at 2, which would be down 2 over 1, 2, 3, 4, 5, negative 2/5. So
That's gonna be standardized stuff.
standardized.
Or did you?
So I have taken what they gave me and made it into a better format because my format is superior. My exam format, I don't know if you've taken exams with anybody else, my exams are just better than everybody else's. If you don't have a cover page, their final exam didn't have a cover page. Come on. A cover page is beautiful. Cover page is excellent. Cover page is lively. But no, so I've written it in my formatting, but it is a departmental exam. I think they do give us a little bit of wiggle room to add extra questions if we want. But why be mean? All right. So I will have office hours on tomorrow. During finals week, I don't have office hours, which doesn't really help us because my office hours are Tuesday, Thursdays. But if you have any questions, please feel free to email me. Otherwise, happy studying. Have a great weekend. Good luck on the rest of your finals, and I'll see you on Monday. All right.